Yeah, before turn to a new example, I forgot to mention this page, one slide. So remember, everything is based on the going back to the very fundamental of statistics and randomness. Everything is based on repetitions of experiment, and we distinguished two subjects, population and sample. So population is a hypothetical and theoretical case when you have infinite number of experiments, which is impossible, but that's what we would like to know and what we would like to infer about. On the other hand, the sample is a finite observation. So you can repeat the experiment for a finite number, and that makes a sample. So it's same distinction applies to the mean or the average. So we call the population mean if you have infinite number of outcome. So if you have infinite number of observations, you know the true probability. You have the true probability, so you can calculate the true mean. So this is the true mean because you know the true probability only when you have infinite number of observations. However, the method 1, raw data does not exist in this case. There must be infinite number of outcomes, which is not possible to add. You cannot add infinite number of numbers, and you cannot divide it by infinity. So method 1 does not work in this case. Just it's a but anyhow, population mean is a purely theoretical, hypothetical object, and we usually denote it as mu. It's a Greek letter called mu. On the other hand, the calculation applies to the sample mean because to calculate something, you have to have something, right? You have to have observations, and it cannot be infinite. So uh, usually you calculate the mean from a sample by construction. So and in this case, as you see how you do it. In this case, the problem here is the probabilities. The probabilities in this table are sample probabilities, which can be different from the true probability. So because the sample probabilities may be different from the true probabilities, the sample mean can be different from the population mean. So usually there is a true mean, but the sample mean has a kind of random error in it. So that's why we need a separate notation, a different notation for sample mean. The sample mean is usually denoted as x bar. Put a horizontal bar on top of x, and this means the sample mean for random variable x. To denote sample mean of y bar, z bar. So depending on the random variable, usually we put a bar on top to denote the sample mean. So this distinction will become much more important later in maybe in chapter 9, 8, or 9. Okay, I have to mention it briefly now. Okay, let's start another example. Now think about, I will consider, of course the data is made up. We would like to evaluate a car dealer's sales performance. By the way, these days used car market is crazy. A few months ago, like a couple months ago, I sold my like 12 years old car about like $7,000. It was a Camry, but nearly one third of the original price. So if you have an unused car that you don't use, your family don't use, then I recommend you to sell it. Consider selling it. It's it's really crazy. Anyhow, so suppose that you are the owner of a dealership, and you hire many car dealers, sales agents, and a sales agent's record in the past 50 weeks. So it goes like this. So so you have 50 observations. 1 week is one experiment, one observation, right? So there are four different outcomes. So among 50 weeks, 25 of them, the agent sold nothing, right? I don't know if it's how realistic it is. I don't know the real distribution, but just make everything simple. Suppose that 25 out of 50, the salesperson does not do anything, does not sell anything, and 20 out of 50 sold one car, and 4 times out of 50 sold two cars. And in a very lucky week, sold three cars a week. So now then my first question is, what is the probability that this dealer, this agent, sells three cars a week? Right? Do the math, do the work. Simple. I will turn the page. 3, 2, 1. So the numbers I gave you in the previous slide was frequency. How many times you observe the outcome out of 50 observations, right? So you can turn the frequency into probability by dividing them by the sample size, which is 50. The total number of observations was 50. So the sales agent sold three cars only once out of 50 weeks, which is 2%, 0.02. So this is the first step to calculate the mean. So then now we have the outcomes and the probability. So we have a probability distribution table. So from this table, you can calculate the mean of weekly sales. What is the average number of cars the agent, the dealer, sold in a week in the past 50 weeks? Try. This is a very important exercise. First exercise to calculate the mean. You have outcome and probability. And remember, the mean is the sum of probability weighted outcomes. So I recommend you to make an additional column right to the table and do the math. Calculate. You may use a calculator, Excel, whatever you want, and try to calculate this. Right? Pause the video and calculate. I will show you the answer. The answer is, what you need to do here is you have to first multiply the outcome to its probability, right? 0 times 0.5. In this case, the weighted outcome is also 0, so it's simple. And 1 times 0.4, 2 times 0.08, 3 times 0.02. So just multiply line by line. Then you get 0 0.4, 0.16, 0.06. These are probability weighted outcomes. Then you got the probability weighted outcomes, then sum them. Sum the probability weighted outcomes. So you get 0.62 cars per week. That's the average. The dealer sells 0.62 cars a week on average, right? So, okay, that's how we calculate the mean, right? So it's simple, just tedious algebra, but the basic principle is quite intuitive. And now I'm going to put a little more context on this example. Let's make more economic assumptions. Suppose that if the agent sells a car, then you as the owner, you get a profit of $3,000, right? You make $3,000 profit, and on the other hand, you have to pay the agent a weekly salary of $2,000. right? So then you have to think about if this salary is worth of the agent deserves that salary. There are a lot of different ways to measure it, to evaluate the performance, but we are going to here in statistics. Usually we compare the expected profit, right? So the agent makes this much profit to me, and he receives this much salary. Then, however, the profit is random. Profit some on some day or sometimes he does very well. He performs really well, but other times does not, right? So to cancel them out, to summarize them as a number, we are going to use the expected net profit. By the way, I'm not saying this is the right way to evaluate the performance, but I'm only saying that this is the most common way to evaluate the performance. Right? Instead of the expectation, there are many possible alternatives, and expectation may have some problems. So I'm telling you that, but still expectation is most common. So let's try this. Let's think about the expected net profit. What we are going to do is we will convert the number of cars into the net profit. So think about this. In a week, in say this week, the agent cannot sell any cars. And then as to the owner, the net profit is the agent made no profit but took $2,000 salary. So the net profit is minus $2,000. On the other hand, if the agent sold 3 cars, then he generated $9,000 profit but took only $2,000 as salary. So in the end, he made a positive $7,000 profit, net profit to me. So sometimes he's not doing well, other times he's really making money. So then, what? How can we compare? How can we make the decision? How can we evaluate this performance? Uh, by the way, what I wanted to show you here is first we are converting this event, selling 0 cars, into making a net profit of minus $2,000. They are the same event. So selling 3 cars a week is the same event as making a net profit of $7,000 in a week. They are the same event. So what I'm doing here is I am recoding the outcome into different numbers, right? Remember, a random variable is a numerical description of the outcome. In the original data, the outcome was described in terms of the number of cars sold. However, what we need and what we want is we would like to describe the outcome in terms of weekly net profit generated by the agent, right? So we are just changing the numbers that describes the same outcome. So it is no difference in the underlying randomness. So their probabilities are the same. As I said, the only difference is instead of putting the name 0 on it, I will put minus 2000 on the same outcome. So I'm renaming all the outcomes in terms of the net profit, right? And then we get another probability distribution table. Remember, the probabilities are the same, only this part changed. I renamed the outcomes into different numbers, different scales. So now you can calculate the expected net profit. Do this. Try this. I will show you the answer in the next video. Do this before watching the next one.